Okay, guys, welcome. Today we're going to talk about exponents. We're going to talk about a bunch of different rules for simplifying exponents. We'll talk about why x to the 0 is always equal to 1. We'll talk about how we can interpret negative exponents. We'll talk about fractional exponents, and then we'll also do a couple of examples where we are given some algebraic expression with exponents and how we can simplify that. Okay, so first of all, let's talk about what we mean by if your exponent is a positive whole number or a positive integer. Now, if you have something like x to the m, all that really means is that we have repeated multiplication, right? So if you have an exponent, that just means repeated multiplication. And if you have your exponent is just some number m, then you're doing that repeated multiplication m times, right? So that's the idea. So for example, if you have x to the third, that's just x times x times x. We need 3 x's there because the exponent is 3. All right, so let's do a couple of examples of that. So part A, we want to evaluate 1/2 to the 4th. So in this context, we could say this is 1/2 times 1/2 times 1/2 times one more 1/2, right? We need 4 of those 1/2s. And of course, to multiply fractions, we just multiply across. So this is 1 times 1 times 1 times 1 over 2 times 2 times 2 times 2. So in the top, we get a 1. And if we multiply 2 by itself 4 times, we'll get a 16. Okay, now in part B, we want to do x plus 2 cubed. And this just means x plus 2 times x plus 2 times x plus 2. Now, to simplify something like this, I usually recommend doing 2 at a time. So if we do x plus 2 times x plus 2, you can check me that that will be an x squared plus a 4x plus 4. And we then want to multiply that by x plus 2. So now we just need to distribute here. So if I multiply x squared by x, I'm going to get an x to the third. X squared times 2 is a 2x squared. 4x times x is a 4x squared. 4x times 2 is a plus 8x. And then 4 times x is 4x. And 4 times 2 is 8. And if I combine all these like terms, I'm going to get x to the third plus 6x squared plus a 12x plus an 8. So that's what we would get when we would simplify that one. All right, now we're going to sort of show the next rule here. Okay, so the next rule explain why if we multiply two numbers with the same base, we add their exponents. Why is that happening? Well, let's check this out. So we said that x to the m earlier was just x being multiplied by itself m times. So there are m of these x's. Well, x to the n is a similar thing, except we have n x's, right? Right. So if we multiply these two things together, we're going to get m x's and n x's. So this is n times. So how many x's do you have total? Well, you have whatever m plus n is. Right, and another way we could say that is that this is just x to the m plus n. Right, so that's the idea, is that if you're multiplying two numbers with the same base, if you add their exponents, that's the equivalent definition, right? Okay, let's look at a similar situation. So now, what if we have x to the m to the n power? Okay, so we claim that that is when you would multiply their exponents. Well, again, x to the m is just x multiplied by itself m times. Now, if I take that x to the m and I raise that to the n power, that means that I need to take this m times version of x, and I need to multiply that by another m x's. And I need to do that until I have n of these groups. Okay, so we have these m times happening n times. So of course, how do we combine them? How many total do you have? Well, you have n groups of m, so this is n times m times. And of course, how can we say that? This is x to the n, sorry, to the m to the n. All right, but of course, multiplication works both ways, so you could switch that if you really wanted to. Okay. Let's look at another rule and figure out why this sort of makes sense. Okay, so we're claiming that if we take x times y and raise that to the m, then that's the same as x to the m times y to the m. Let's see why that's true. Well, x times y to the m is xy times xy times xy, where there are m of these. All right. Now, one thing that I want you to remember is that it doesn't matter the order that you multiply numbers, right? If you take 3 times 2, that's the same as 2 times 3. So the order doesn't matter when you multiply numbers. So I could have said that this is x, all the x's first, where there are m of them, and then put all the y second. So there are m of these. All right, but what does that mean? This means that I have x to the m times y to the m. So we can say that this rule, of course, is true now because of that. Okay, so that's another exponent rule. All right, so basically we've shown these three properties here, right? So if you take two numbers with the same base and you multiply them together, you add their exponents. If you raise something to an exponent to another exponent, or power to a power, I'll frequently refer to that as, then you multiply their exponents. And then if you have a product of numbers to the same exponent, that's the same as the product of those numbers all to that one exponent. Okay, so let's talk about zero power. Okay, so anytime that you have something to the zero, as long as this isn't zero, that's always equal to 1. All right, and what we can really say about that is, let's put it this way. So let me try and prove it to you. So let's say that we have x to the m divided by x to the n, or something like that. All right, well, anytime you have something over itself, that's just equal to 1. Right, so x to the m over x to the m is equal to 1. Now, I could have also written this, we haven't really talked about this yet, as x to the m minus m. If you divide, then just like we had, if you add if you multiply two numbers, you add their exponents. If you divide two numbers, then you subtract their exponents. So this is the same as x to the m minus m, and of course m minus m is 0, right? But these two things are equal, so these two things are equal. So that's one usual way that we can talk about how x to the 0 is equal to 1. Okay, now the next thing I want to be very clear on. So if you have a negative integer exponent, what you can do is move that from the top of a fraction to the bottom of a fraction. Now, the way that most books present this, I'm usually not a fan of, because usually your gut reaction is to say, well, what's really happening here? You're flipping it, all right, which is not necessarily true. I typically like to think of it as, if you have a negative exponent, it's going to move something from the numerator to the denominator, and vice versa. If you have a negative exponent in the denominator, it would move to the top and become positive. All right, so I typically prefer that way of thinking of it. All right, so let's see what I mean by these negative exponents. So if you have 3 to the negative 2, you can think of that as 3 to the negative 2 over 1. And I want to move this to the bottom to make it positive. So that's 3 squared now. All right, but if you have nothing left up top, we want to put a 1 there. But of course, what's 3 squared? It's 9. So 3 to the negative 2 is 1 over 9. All right, or you can think of it as 1 over 3 squared again. Okay. Now, for example, I want to look at the two graphs. This first graph is x to the negative 1, and this graph is x to the negative 2. Now, why is this one positive and negative, but this one is just positive? Here's why. Because x to the negative 1 we can write as 1 over x to the first, or just 1 over x. Now, this can, of course, be negative, right? This is taking 1 and you're dividing it by larger and larger or smaller and smaller numbers. And, of course, this one is 1 over x squared. And, of course, that can never be negative because you're taking a number and you're squaring it. So that's why you're seeing both positive there. Okay. So now we can talk about fractional exponents. Okay. So one thing that we need to be clear here is that these fractional exponents are sort of related to roots, right? So if we say that we have something like x to the 1 over m, that really means that we're talking about the mth root of x. Okay. Now, what do you mean by an mth root? Well, for example, you could say that if m is 2, you have the familiar square root. Of course, we usually don't write the 2 outside there, but if you want to, you of course can. But if you don't see the number there, we usually assume that the type of root is a square root. Now, what does it mean to be a square root, for example? That means that if I take that x and I square it, that square root of x, and I square it, I am going to get x, right? So what does it mean to be an mth root? It means that if I raise it to the m power, I get x, right? So that's sort of the idea. Now, one thing that we need to be clear about is that if your number that you're taking a root of, if that m is, so if the number that you're taking a root of is negative and you're taking an even type of root, that's undefined. Because, for example, you can't have a square root of a negative 4. Right? Why can't you have square root of negative 4? Because there's no number that if you square it is going to give you a negative, right? That can't be solved, at least not with real numbers. Okay, now if your number under there is negative, right? So if you have, for example, a cube root of negative 8, this is fine. This is just negative 2, right? So because negative 2 times negative 2 times negative 2 is negative 8. So if you have an odd root, that's totally fine. So if your number inside is positive and you have an odd root, then it's the positive version of the number. But in the odd root case where you have a negative number, then your solution is just the negative number. All right. Now, here we want to know, how should 8 to the 1/3 be defined? Well, there's a couple different ways you can think of it. You can think of it as it's the number that if I raise to the 3rd power would give me 8, or you could take 8 to the 1/3 and convert it to that form we just talked about, and that would be the cube root of 8. All right. I typically prefer this way to do it. It's a little bit more straightforward because this is really just going to give you the same thing. To solve for x, you'd cube root both sides, and then you get that it's a cube root of 8, right? And of course, this is just 2. Why is it 2? Because 2 to the 3rd is equal to 8. Okay, so that's the idea there. What about 9 to the 1/2? Well, again, this is the number that if I raise it to the second power this time, gives me 9. Or you could think of it as 9 to the 1/2 is the square root of 9. Right? So of course, you would solve the same way. You'd square root both sides and you get that x is square root of 9. And in either of these cases, you get plus or minus 3. All right, so you get two solutions here. All right, what about negative 9 to the 1/2? Well, this is the number that if I square gives me negative 9, or if I convert negative 9 to the 1/2 into this form, it should be the square root of negative 9. Of course, this is a problem because you can't have either of these. Can't have you can't square something and get a negative number, and you can't take a square root of a negative number. So you can't have either of these, and this is your undefined case. Okay, so this sort of highlights that thing that I wrote earlier. You can write that a square root is the same thing as a 1/2 power, and then if you have a different number there on outside of that root, say it's m, then it's x to the 1 over m. All right, so you could have a 5th root, 7th root, 99th root, whatever. It would just be indicated by a little number sort of outside that root there. Okay, now the next rule that we're going to talk about regarding roots is the product rule. So for a product, right? Now here they're talking about that this is a square root, but it could work for any kind of root. And that says that if you have square root of x times square root of y, you can combine them under the square root, and it also works just as well in the opposite direction. If you have a number that you can break into two numbers underneath a square root, then you can separate them with their own square roots. All right, now this rule is of course very important for simplifying radicals, which we'll probably do along the way here. But I have included a quick example here. For example, if you want to simplify a square root, first you want to break that number m into two numbers where at least one of these numbers is a perfect square, right? And then of course you'll write the square root of m as a square root of a times b, which by this rule you can write as square root of a times square root of b. Now since one of those numbers is a perfect square, you can take the square root of it. And of course, if you can do it again, you would repeat this until you can't anymore. Now, let's look at the number square root of 50, for example. If you have the square root of 50, we can write that as 25 times 2. And of course, this is good because 25 is a perfect square. So once you take the square root of 25, you do get 5. And the square root of 2 is just sort of along for the ride. Now, if you broke it up into square root of 5 times square root of 10, that's valid as far as breaking up 50 into two numbers, but the problem is that neither one of those is a perfect square. So it's not particularly helpful to write it that way. So the key step there is you need one of those numbers that you're breaking your original number into to be a perfect square. Okay, so let's look at another example of this. So if we want to simplify square root of 2 times square root of 6, what we can do is we can write that as the square root of 12. All right, but can we break that up? Well, let's think about that. Can I write this as two numbers where one is a perfect square, or at least one of them is a perfect square? And of course, the answer is yes. 4 is a perfect square, and we can write it as 4 times 3. So this is square root of 4 times square root of 3, and square root of 4 is just 2. So we get 2 square root of 3. All right, so that's one way that we could write this. Okay, now this next example, we want to show that if I take the square root of 4 square root of 3, we get 2 plus square root of 3. All right, now this is a little bit tricky. What's this saying? This is saying that the square root of this number is equal to 2 plus square root of 3. Now, one thing that you might be able to do, This left side has square roots of square roots, so that's going to be a little bit complicated, but let's square both sides. Now it just becomes equivalent to show that if I have 7 plus 4 square root of 3, that's what I'm going to get if I square 2 plus square root of 3. Okay, but what happens if I square this out? 2 times 2 is 4. 2 times square root of 3 is 2 square root of 3. Square root of 3 times 2 is 2 square root of 3. And square root of 3 times square root of 3 is square root of 9, which is 3. And if I combine my like terms here, I am going to get 7 plus 4 square root of 3. So of course, we've shown that the left and right sides are equal. So of course, these two expressions are equal. Okay. Now, I've sort of already alluded to this, but if you have something to the m power and you want to undo that power, you want to find the inverse of taking something to the m power, that's just going to be accomplished by taking the mth root. All right. So you have m power and mth root are sort of inverses of each other. And we've used that property already. We've talked about if you have something squared and you want to solve for it, you need to take the square root. All right. So that's sort of the same idea there. Okay. So now we can extend this to any type of fractional exponent. Okay. So if you have x to the n over m, whatever number those are, this is the same as taking x to the 1 over m to the n power, right, by your power to a power rule. And this is really saying that it's the same as the mth root of x to the n power, right? Sometimes it's also helpful to think of it as the mth root of x to the n with the n on the inside, but usually that's the more helpful way to think of it, is the nth root of x, find that, and then it's all to the n power. Okay, so let's look at a couple of examples of these. So for example, part A, we want to find 16 to the 3 over 2. Well, this is just saying, by that rule, what type of root? That's indicated by the number in the bottom, so that's a square root of 16. And we want to raise that to the third. Well, the square root of 16 is 4. And if I raise that to the third, that's a 64. Part B, we have 27 to the 2 over 3. Well, by this rule, this is a cube root of 27 squared. What's the cube root of 27? I need a number that if I multiply by itself 3 times gives me 27. If you think about that, you'll find that that number is 3. And of course, if we square 3, we'll get 9. All right, something a little bit more tricky is what if you have 16 to the negative 3 over 4? Well, we said that if we have a negative exponent, we need to move it to either the top or the bottom, wherever it's currently not. And now we have something we can deal with in the bottom here. So this is 1. Again, the number in the bottom of the fraction tells us the type of root. So this is a 4th root of 16 to the 3rd. So a number that if I multiply by itself 4 times give me 16, you'll find that that's 2. And of course, 2 to the 3rd is 8. So this is all a 1 over 8. Okay, part D, we have a 27 to the minus 4 over 3. So first, let's deal with the negative exponent. So this is 27 to the 4 over 3. Now, if I write this in the appropriate form, again, the number on the bottom of that fraction tells me the type of root. So it's the cube root of 27 again, all to the 4th. So we just said that the cube root of 27 was 3. So this is 1 over 3 to the 4th. So this is 1 over 81. Okay. Now, part E and F are interesting because part E, we want to simplify t to the 3rd, all raised to the 7 over 3. Well, here we just use our power to a power rule. So this is where we multiply the exponents, and we have 7/3 times 3. Well, what happens here, and you can do this one of two ways. You can think of 3 as 3/1 and multiply across, and you'll get t to the 21/3. Or you could say that your 3 and divided by 3 are going to cancel. Either way, you're going to find that this is t to the 7th. All right, and finally in part F, we want to simplify b to the 1/5 to the 15th. And of course, if we use our power to a power rule, this is, again, we just need to multiply 15 times 1/5. And again, either way you do this, you could say this is 15/5, or you could cancel out the 5 with the 15 and make it a 3. Either way, you're going to get b to the 3rd here. All right, so that's simplifying a couple of those exponents. Okay, so these are all of the exponent rules that we've talked about and an additional few. So these are the ones that we've already talked about. And we also have these two sort of extensions of ones that we've already talked about. So if you take two numbers with the same base and you divide them, we talked about this, you're going to subtract their exponents. And you can also say that if you have x to the p over y to the p, right? So if you're dividing two numbers with the same power, you could have just as easily said that that's first divide the two numbers and then raise it to the power. All right, so let's do an example where we're going to simplify an expression that looks horrible. All right, so let me just write this so you can see it a little better. So we want to simplify the expression x to the -3 times y to the 4th, all squared, over x to the -9, y to the 3rd, and then the whole thing raised to the 2/5. Now, usually with something like this, it's much easier to simplify the inside and then work your way out. So easier to start inside and then work your way out. Okay, so let's go inside. Very furthest inside we can go is this set of parentheses here. So if I deal with that first, so let me just put everything else in black that I'm not doing in this step. This is our product to a power rule, right? So I can take x to the -3 and times that by 2, so that's x to the -6. And then y to the 4th squared would give me a y to the 8th. Now let's deal with the negative exponents. So now let's take my two x negative exponents, and I need to move them. So the x to the 9th in the bottom, x to the -9th in the bottom will become x to the +9 in the top. And x to the -6 in the top will become x to the +6 in the bottom. And now we haven't done anything with 8, y to the 8th and y to the 3rd. Okay, so now we can look at each of our two terms separately. I can look at my x terms together, and I can look at my y terms together. Now, x to the 9th over x to the 6, this is our subtraction rule. So this is x to the 9 minus 6. And same thing with y. I have y to the 8 minus 3. And this is all still to the 2/5. So now if I simplify them, I'm going to get x to the 3rd, y to the 5th, to the 2/5. So finally, we just have to now apply our power to a power rule as well as our product to a power. So this is x to the 3rd to the 2/5 times y to the 5th to the 2/5. So my x is going to become x to the 3 times 2 over 5. And my y is going to become 5 times 2 over 5. So now for my x, I have x, and then I need to multiply there, so I'm going to get a 6 over 5. And then for my y, the 5s are just going to cancel. I'm going to get y squared. And we can say that's our final answer. All right, so that wraps up this video on exponents and properties of exponents. I hope you enjoyed, and I will see you next time.